Thank you very much. I will start with this slide here, just briefly to actually, it's a very good slide to start with in the sense that it shows a number of the different types of buildings that we do. I'll introduce myself first. My name is Marc Zobec. I'm the Director in charge of Technical Support, Research and Engineering for the Permasteelisa Group. Just a brief background on our company is the Permasteelisa Group is a company who specialises in building systems, not only facades, but all sorts of things. Produces in excess of 20 million square feet or 2 million square metres of surfaces annually, with a turnover in excess of €1 billion. And the main thing what I want to try and show with this slide is the different diversity of the type of projects that we do. And the main thing also by showing this slide and showing the different diversities, the emphasis what I want to try and show is that as a company, we are not a product company. We do not have a catalogue. We cannot show you a system that you can buy standard and such. We specifically engineer a solution. And so what I really wanted to show you today was in the complexities of what we call now the current trend of free form or fluid form architecture, how does one go about procuring one of these facades? How do you actually design it? How do you actually build it? How do you bring it in on budget and in time? And one of the main things is what I want to look at and try and show you today is the approach that you take to the procurement of a facade, and also the facade itself, the way you need to look at it in the design aspects. Is it really surface? Is it substance? Or is it system? Basically, one of the interesting points that came up in our last session was we discussed about the procurement process. We were discussing about at what point does the facade contract actually come into the foray into the design. It's very interesting to note it's very much a cultural aspect. It very depends on where you're working, the people you're working with too. But in our experiences, doing these type of buildings, these type of curved, twisted, or irregular form buildings, you have to have not only an open-minded approach or thinking out of the box approach, not only the technical aspects of the facade, but more so to the contractual aspects of the way you want to procure the facade. So one of the first things which I would like to show is firstly the variation in the procurement process, where normally with the standardised procurement process you would have a predetermined specification where your technical criteria, materials are determined, your testing program is established, mock-ups and such. And then from there you would have a predetermined design documents. Designs would go out with design intent, let's say, what you should follow in terms of modulation, sizes, what the architect would like to see, or also the owner. And then more so you go to tender stage. In a tender stage you go out and at that aspect many times you have very limited design options, particularly if it is a irregular shaped building. Now, one of the interesting things I saw also in the previous session was a lot of the effort that goes from the architecture, or the architect trying to actually establish the surface, defining the surface and the background to that surface. But in the projects that we've done and the success of the projects that we've done, the main success has always been where we've been able to have an iterative or a collaborative approach with the actual architect at a very early stage. One of the problems with the standard procurement process is what we generally see quite often is these specifications that are written, and you have a specification written for a particular type of the design, and quite often the specifications that we find are very much so, and I look at the word specification because the first part of it is written specific, and very much so they're not very specific, and they are what I call cut, copy, paste type specifications, where you see the same format of specification appearing time and time again. For a building which is very irregular, if the specification is not well written, we believe that you do expose yourself very much to cost and contractual type of problems in the future. As opposed to this, if we do a complex type of facade, the success of the type of jobs that we've carried out is more so it has adopted what we call a two-stage tender process, where at the first stage there is a pre-construction agreement. So what happens is the facade contractor will come on board and will work in collaboration with the architect, because quite often the surface of the building in question, with slight adjustments, with slight variations, with slight changes, you can much more often you can come up with a great deal of savings, because you can actually adjust the actual system itself, you can adjust the modulation, you can maximise the type of glass areas that you're using, the surfaces that you're using. And so the most successful ways we've seen is having a collaborative element of design. And when that design is established, then what we try to do is we try to write specific specification for that design. At the same time developing quality manual, quality procedures, budgets, and as well as value engineering types of options. After this, if the client is so pleased with the design, as the architect we can then enter into a construction contract process, which is can be done in negotiation, or at that point you can choose to retract the documents. You can go up to the normal type of a standard procurement process. I will try and show you some of the different projects too that we've done. I'll actually take you through a case study to actually show you exactly what I mean, how we actually went about this. So with a pre-construction scope of work, generally what we try to do is obviously get the general project concept and have a geometric review. First thing is to go through, look at the geometry, look at the surface, try to see if there's any anomalies, highlight and bring up to the architect, to the owner, any problems which you may foresee, be they logistical problems, be they design problems, be they problems that will maybe cause time or even cost overruns. The second thing then obviously is the COCO system development. This is very important. Why I mean the iterative process is because from here, by being able to look at the system that you wish to adopt, very much so, you will then have to go back into the geometry and see whether the system that you have can cope with the geometry changes. So this is where you have the back and forth process in the very early, what we call the two-stage tender process. After that, you have to develop the geometric limits in the technical specifications. So if you have a building which has a complex surface, a complex, a surface or a shape or a regular surface, what we're trying to do then is we try to actually then establish what are the rules, what are the limitations, what can the architect work within. We don't want to try and just have one fixed set of rules or one fixed set of constraints fixed in stone. What we want to try and do is actually give some variation, give some freedom, but yet have a system which can cope with a number of variations and changes. And then beyond this, as I said before, we will write them or we will develop together a specific technical specification specific to that actual design solution. After this, we'll finalise the surface and the wireframe model. So we'll fix those we'll fix those and have those signed up. And after this, then obviously you'll enter into the construction contract scope of work, defining what areas you actually need to look at in a general format. A series of formal submittals actually have to be then in place. Production engineering needs to commence in the sense of now that we've got the design and we've got the information, what do we actually do with that information? It's very interesting that I saw the professor from Tokyo beforehand, where they actually tried to measure up the very different types of dimensional constraints on this actual building, rather than actually having a model, which he did explain. Yes, you could have taken the model, you could have taken some of the surface points in the geometry, but what we more than likely what we try to look at is, if we work with the architect at a very early stage, and the collaborative stage, what's very important is to understand that the digital representation that you have is not just what I call pretty pictures or graphical representation. You want to try and have data that is produced which in itself becomes actual data that can be downloaded into very different types of sources of material procurement, material machining and such, and I'll show you exactly what I mean by this in the case study. After that, obviously you enter into the fabrication and assembly stage, and obviously the installation and the handover to the client. The case study in question, what I wanted to show you here is a project called USA Interactive. For those of you that know, it's located in New York on the western side of Manhattan Island, near Chelsea Piers. It's a project by Frank Agarian Partners. The interesting thing about this job is that in typical Frank Agarian fashion, there are no straight surfaces. It's very fluid in its form. But more so, what was the most interesting thing about this project was that the actual entire building was first Agarian in the sense it was glass. It wasn't titanium, stainless steel, it was purely 100% glass. And the thing about it was how do we realise a building with glass, particularly with so many curved surfaces, and how do you get it to a very cost-effective system, and how do you actually deliver that on time and on budget? One of the things that we looked at here also was looking at the type of material, glass as a material itself, and what are the constraints of glass. In essence, if we look at the structure of what I just showed you there with a scroll through of various photos, it's basically a helix type of form, and in essence what it does, it twists through itself. So through about 27 floors, albeit the building's not that tall, through 27 floors you actually completely twist the building 90 degrees. So one of the first things that we had to look at, the general project concept and the geometric review of the actual building. We wanted to look at all the surfaces, see what the constraints were, and what the actual surfaces were doing. So we looked at the surface as the curving system developed, and we had to look at the way the actual geometry changed, not only in height, in the curvature, but also in plan. And the objective here was, with the design, was whilst the surface was curving, we wanted to make sure that we could minimise the cost of this building for the client. So what we did not do is we did not use any curved glass, so to speak. We did have a curved building at the end, but we didn't curve the glass in the traditional sense. So what we actually did here was we did a process which is called cold bending. And in essence what it was that we saw this on the line when we were producing panels. Panels would come off the line, you'd grab three corners and one end would dip, or you'd grab a piece of glass, it would sag. So glass is with many other materials, as long as you can use it within its elastic range, it is a material which is deformable. So what we were thinking was, why not be able to use glass like we've done in previous projects where you would form into flat metal type panels. Whatever you could do with metal panels, why could you not do that with glass? But obviously this had a number of constraints that we had to look at. We had to look at obviously the geometry, we had to look at the surface in itself. And one of the main things also, look at the component design, we had to look at the amount of changes in the angles of the actual facade itself and how we could actually slightly tweak the surface itself with the architect in order to actually minimise the number of different types of extrusions and panel types itself. So we actually did in the system development obviously was, we looked at a panel here, if you look, we produced a flat introduction, but what we did was when we installed it with three sides and physically pried and in to produce the curved surface of the glass. The main thing what we tried to do also was very good here was the type of software that we adopted here was a parametric design software, and what it enabled us to do was model in real time and actually model the actual interfaces between one panel and another. For those of you that are not familiar with parametric design, essentially it's different to systems where you actually layer designs on top of each other for graphic representation. With a parametric design system, a point in space is actually data. Another point from any object can occupy that space without affecting anything around it. So in essence, if I have a system and I want to introduce two mating elements together, if they cannot actually physically bring them into the computer model. The other great thing about this is if I have numerical data from the model that I use, then the numerical data I can use in many other aspects. I can use it for cross control, we can use it for numerical machining, we can use it for purchasing, you can use it for tracking other materials, you can use it in many, many other aspects, which I'll show you. So as I said, we produce flat panels, deform them in a shape. One of the main things that we have to look at here was what actually happens to the glass when it actually bends in shape. So one of the things we have to take out a lot of engineering analysis, also look at the thermal aspects of the facade as well. We have to look at, we carried out a lot of stress analysis on the actual glass, on the interlayer itself, to try and see what was going to happen with the glass long term. And particularly when you're working not just with glass, but you're working with glass which is laminated, and also it is within a double glazing unit. So what does it do to the PPB? What does it do to the actual silicon seal that holds the glasses together. What does actually do to the butyl on the perimeter of it? And what's going to happen with the long-term warranty of that glass? So we looked at the system. We carried out some analysis. And one of the interesting things we were looking at is a lot of those materials were very time and strain dependent. So you did stress them. They would stress up to a certain point, but what would actually happen with time? So with some modelling and testing, what we actually were doing, we found out that, for example, the PDB, if we were to deform that in one area, immediately it would set up stresses, particularly in the corner. It would be bent points. But with time, as the material would tend to creep, you would see that the stresses would relieve. So we could maintain the surface without having these high stresses in the glass if they would relieve. The same thing we did this on the silicon seals on the edge. We wanted to seal what type of stresses were. Was there going to be a breakdown of that so that in the future the double glazing unit, the integrity of that air cavity was not going to be compromised? So looking also, we developed a series of technical specification and a geometric rule development. So in this instance here, we had a certain rule for how much we could actually bend the glass, how much we could pull it back, how much we could twist it, turn it, and slope the glass in various. So we looked at the maximum twist of the mullions, we looked at the allowable angular inch for vertical mullions, the rotation at the stack or at the joint from each floor of the actual panels. We also looked at the required glass layout, what type of panel we were looking at, what was the glass geometry, could we get some sort of economy of scale from the types of glass that we're using. And we also were saying that, okay, if we're using triangular units, we will not have any twisted units with the triangles. That's just some of the sets of rules that we did use. Now, with the curve wall system development, once again, we had to do proof of concept testing again. So, taking these types of panels and bending them, I know that one of the questions is going to crop up, and this is why I put this slide in there, is only what would happen if you had to replace a piece of glass? So what would happen is, how would you actually put it in? So one of the things that we actually did was we set up these panels. We actually put, the three corners, we fixed them in, pried in one, we put in a load cell, and we measured actually how much force it would take to actually push that piece of glass in. And not so much how much force you needed to do for the replacement, also what it would do on the actual seals and the silicon, particularly the structural glazing long term. So, with the technical specification, we looked at the maximum minimum glass sizes as well. And then we looked at the requirements for a 3D wireframe model. So as I said before, it was very important that the data that was produced, what was produced was not pretty graphical images, but very much so data that could be interfaced between us and the architect, and then more so from us to the machining and to the actual production processes which we adopt. And to be able to do this, what you can actually do then is you can actually then understand that what it is about. It's not about standardization of the material or standardization of the product. What it is so much, if you want to bring these type of projects in and make them cost effective, it's about the standardization of the process. It doesn't matter if you have so many irregular panels, the main thing is that you can actually issue the way you actually carry out the actual design. Look at the modulation and etc. Quickly just going through here, I'll show you. We finalised the surface geometry wireframe. You can actually see from the model on the left-hand side, that's the surface as it's changing. We took a wireframe model of this so that we could get the actual modulation. We imported these systems, and we then developed our own, what we call our own editor software. It was interfacing software. So what we could then do, we could generate a unit geometry based on the building wireframe. Then we could look at the component makeup and the geometric uniqueness, and then we could optimize this output to CNC fabrication. And not so much for fabrication, but also for production. And also for tracking, a bit like you have your DHL type system where you actually know where effluent is, where it is in terms of its delivery, whether it's in the panel, whether it's going to site, where it is being installed in the building, you can track it all the way through. So this works for complex buildings, but there's no reason why it couldn't work for standard buildings as well. So going through again, showing you the editor software here. The interactive core, as a case study, you'll see 98,000 square feet, not a overly big building, but nonetheless, it's quite complex. There was 35 custom extrusions. Now, 35 custom extrusions in a building like this is nothing. You can have multiples of this for for normal standard type of buildings. So we were able to minimise the actual different types of extrusions. There were two sets of mullion pairs only. They could go from a range from -3 to 14-degree rotation. The horizontal could stack, go in and out 5 degrees. And this is when I'm talking about this degree. This is sequential. It's actually each panel to each other. Now these statistics are staggering because there's 1,440 units, and more than 90% of these were unique. 21,000 components, of which 15,000 were unique. 86,000 components in total, and 318,000 uniquely parameter values. It's staggering. But what if you could actually utilise the data correctly, have a computerised system of managing this, it is very easy, it's very simple, and this is where you can actually make this actual savings and deliver the projects on time. In the end, we produced 146 gigabytes of data on this project. The whole project was done as a computer model. There was no paper submissions other than if you needed it on site for convenience. So the process overview, once again, we took the CAD model, was imported region by region. We took it to a SQL Server database. And this system then allowed us to provide an interface to navigate and manage the unit data. What this allowed us to do was we could actually take the units, we could actually number the units, we could look at what the similar type of units were, we could look at what the actual different types of units were, we could actually number them, we could get components, we knew where the production lot assignment was, where that unit went on the building. The creating info, we looked at where the similar type of components were. So if you did get some similar components, during the machining process you could make sure you must that as well. We looked at the component assignment, where you would assign that in each building. So essentially what we're doing is we made like a Meccano type set of drawings where you actually look at the actual units itself and all the pieces that go within it. So the unit configurations are identified. You can see that there's certain codings on this. With units with identical configurations, they're assigned to the same assembly model solver. So what I mean by the assembly model solver, I'll show you in a second. But as you see, there's certain lots of units identified. You can actually see the actual types of what that actually means, whether it's the middle of the wall, the type of bracketry that we use, primary profile, and also we look at the different types of specials, the parapets, the outside corners, the anchors, left, right, and also the profile code as well of the system. Then what we do is then we take this, we then generate, in this instance we use CATIA, we generate the model, but because it's parametric, what we could actually do was generate this in the model solver so that for different geometry, using the same components, you can actually just adjust the actual geometry, and from there you will automatically have a three-dimensional solver which will then use the parametric data to actually adjust the actual system itself, but more so to take that data and prepare it for your machining. So from here, it enables us then to solve the units. They're inserted also into wireframe. So as I said before, the parametric data, we actually then assemble the full building. You can actually build it. It actually all goes in. Which ensures the quality, CNC output. Then we import this into the SQL server. It goes then back into the CNC machine, automated computer cutting. It's a high degree of automation and gives you a high degree of quality in fabricated components. Some of the successful projects that we've done is at Barcelona with a similar system. Look at Guggenheim Museum, if everyone's familiar with Disney Concert Hall. The Millennium Bridge here in Chicago, you've seen that. Other projects coming up, Jade Ocean in Miami, as well as the Art Museum in West Virginia. Now, I'll just summarise quickly because these are just a set of rules. So for anyone here who wants to try and procure one of these facades, from our experience, this is the way we've found the best way you can bring this in on time, budget, and provide the warranty for your client as well. Firstly, what we're talking about is you think out of the box, not only technically, but more so contractually. Adopt a different approach, not the confrontational type of approach, but get a collaborative approach. Take that collaborative approach to procurement and not make it contractual. Make the contractor part of the design team if possible. The greatest risks on these jobs are not technical issues. I think they can all be solved. The biggest risk, like for any job, is your time, cost, warranty, and the management of these. You need someone who can actually manage all this data that is going through. You need to focus on procuring technical know-how. Look at it as being technical knowledge that you're looking at, not materials and labour. That can be procured anywhere. Ensure the contractor knowledge has it in-house and it's not outsourced. There's nothing worse than actually having all this information interspersed all over the place and you don't actually know or you cannot track it. The project risks and costs can be minimised by standardising processes and not only the product itself. Free-form buildings also don't necessitate invention, but more so you look at innovation. You don't have to bring out new products, you only have to innovate the ones that we use. And in doing so, we have to develop the design by practical application of engineering principles, not blind adherence to standards. I'm sick and tired of people telling me that this is what the standard says. Well, we also always have to understand that standards are a minimum requirement. It's not the gospel truth. Adopt the parametric design software, so aim to produce digital design data and not just graphics and images. Apply specifications and standards as a minimum, as I said before, and not as gospel. Set up specific specifications, specific as in the word specification, or a specific solution. Avoid those cut, copy, paste steps that you see all the time. That leaves you very, very open to claims, and extras and costs. Engineer materials to their fullest potential. It's never been done before, mentality doesn't mean that it cannot be done. Have an honest budget prepared in conjunction with a contractor experiencing similar work. Do not apply standard rates. It's one of the worst mistakes that can be made. Follow the two-step tender process where possible. In our experience, it is the most successful projects coming on time and on budget. Remember, on these type of projects, you only get one chance. The failure of the contractor makes the project extremely difficult to follow and recover. At that point, I thank you for your attention.